So welcome everyone. We are now in on Thursday of week 9. So this will be the 18th of September 18th. Oh, hello, Daisy's dog. Oh my god, you're adorable. Oh, who's a good boy? Who's a good boy? Of course, I'm recording now, so that was a little embarrassing, but okay. Anyway, so we are now in.
Her name is Lola.
Her name is Lula.
Yeah, Lola.
Oh, okay, Lola. Lola.
Mhm.
Oh, kudos to you for originality. I haven't heard that name before. But anyway, so we are now recording. I'm going to share my screen. And here we are on variability. Okay. So statistics has often been called the study of variability in data. Okay. In real life, in math books everywhere, they give you a question and they say, you have a field that's 18 square acres or whatever it is, and those numbers are exact, precise to the infinite decimal place. But in reality, in real life, we never get situations like that. We never get perfect numbers. What do? We take data, and from the data, we um, we analyze the data, we examine it, we infer things from it, we come up with a value for whatever we're looking for from the data, but it's never going to be exact. We can measure the same thing 100 times and we're probably going to get 100 different results because there's always going to be some variability in your data when you record something. So statistics is the study of said variability. Okay, so let's look at this example here. We have two basketball teams. We have the team in white and the team in green. And they're given all their all their heights in both feet and inches, and in inches alone. And of course, inches alone are better because it's not a mixture of two different units. So it's a lot easier mathematically to do with them. And what we want to do here is we want to compare the means and variability of the heights of these teams. So let's first compare their means. How do you take the mean of a set of data? All right, we have two sets of data here, so we have two means that we're going for. How do you find the mean of a set of data? This is open to the whole class. Don't think I'm only talking to the person next to you. Okay, so anyone, you're free to answer this. How do you find the mean of a set of data?
You add them all up and then divide by the number of what you added.
Yeah, you add them all up and then you divide by the. Do these guys know that they're going to be on YouTube forever? I mean, if they did, they'd probably like prance in or something like that. They won't just walk and like, oh, this interesting. Anyways, so what do? You add them all up and you divide by how many you have. So let's do it for the first one. Let's all calculate the mean. So you should all take out your calculator, which of course you all have because this is a math class and nobody comes to a math class without a calculator. That's just an amateur move. So let's go ahead and calculate the mean of the white jerseyed team. You add them all up and you divide by how many you have. What is the mean of that team? How many inches?
75.
X bar equals 75. And I'll say it X1 bar to indicate that this is the first mean. And now we want to calculate X2 bar, the second mean. So what are we going to do here? We're going to add them up and we're going to divide by how many they have again. And what do you get?
75 again.
75 again. So they have the same mean. But let's look at the two teams. What do you notice about the heights of the team on the left? What stands out about their heights as opposed to the heights of the team on the right?
They're roughly about the same height.
Yeah, they're all roughly about the same height. There's not that much variability in their heights. If you look at the actual numbers, they're all, for the most part, pretty close to 75, right? A few up, a few down, but they're all pretty close. What do you notice about the variability of the team on the right?
There's an outlier.
Well, not just an outlier, but there's a lot more variability, right? They have the same mean, they have the same average, but they vary by different amounts. And that's the key here, is that we want to be able to compare two data sets, taking into account that when we deal with variability, when we deal with means alone, you lose a lot of information because the variability inherent in the data is kind of left out. And we don't want to leave it out. In fact, it's the opposite. We want to include it. Okay? So let's see how we do that. As we're going to see, by the way, there are 4 different measures of variability. And we're going to use really 2 of them. 2 of them are used as an introduction, and then we're going to throw them away. So we're going to end up with 2 that are actually useful. So let's first look at the Common Core standards, because again, what's going to happen, you guys are going to be teaching eventually, hopefully, kids, and therefore you're going to need to know the curriculum for your age group. So the California Common Core State Standards has this goal for 6th grade students. Students recognize that a measure of variability, whether it's the interquartile range or the mean absolute deviation, those are 2 of the 4 that we're going to see today, can also be useful for summarizing data, because 2 very different sets of data can have the same mean and the same median, yet be distinguished by their variability, like the example we just saw. And here we have a standard for Algebra 1, which is probably maybe 9th grade or 8th grade. We're going to use statistics to appropriate to the shape of the distribution to compare the center, either the median or the mean, and the spread, again, either the interquartile range or the standard deviation of 2 or more different data sets. So the interquartile range, the mean absolute deviation, and the standard deviation, those are going to be the 3 that we are going to end up using. Okay, IQR, the MAD, and the SD. Okay, the IQR, the MAD, and the SD. So first, why not the range? Okay, the range is the highest minus the smallest. The highest minus the smallest is seems to be a pretty decent measure of how spread out the data is, right? Just take the biggest, take the smallest, subtract them, you have the range. The range is the number. You don't say, oh, it's 2 to 10. That's not the range. The range is 8. The range is how spread out the data is, biggest minus smallest. So why don't we use the range when it comes to a measure of variability? And the answer is because it's just not very good. Look at these 2 distributions here. The highest is 23, the lowest is 13. And here the highest is 23 and the lowest is 13. So they're going to have the same range. But the first one, the data is kind of all over the place. The last one, all the data is on the wings on the far right. And if all we do is we look at the range, we don't really get an idea of true variability of the data. So the range is just not very good. Plus, it's very sensitive to outliers. You make one outlier and bam, the range changes, because now we have a new max or we have a new min. So it goes up, significantly. And we don't want to have a measure of spread that is sensitive to 1 or 2 outliers that are all over the place. Okay? So no one actually uses the range. Nobody does. They might say the values range from 13 to 23. They might say that, but no one says, oh, the range is 10, as if that means anything. Okay? So yeah, we want to know where the values are. Oh, the values start here and go here. But in terms of the range itself, which is max minus min, we just don't use that. So it exists as a measure of spread, but it's not used as a measure of spread. So then we have the IQR. Okay, the IQR is really our first true useful measure of spread. It's not max minus min, but it is Q3 minus Q1. Okay, it's the third quartile minus the first quartile. In terms of this example here, what is the range of this box plot? Not the IQR, which we like, but the range, which we don't. What approximately is the range in this situation?
110 to 118.
Sorry?
110 to 118.
No, the range is max minus min.
Oh,
All right, the range is the highest minus the smallest. So what's the highest?
135.
134 it looks like. And what's the min?
100,
100. So what's the range?
34.
The range here is 34, biggest minus smallest. But what's more useful is the IQR. The IQR is biggest minus smallest. Sorry, that's the range. My bad. The IQR is Q3 minus Q1.
What does Q stand for again? I'm sorry.
IQR, the interquartile range.
Quartile.
So what is Q3 in this example?
The 118.
About 118. And what is Q1 in this example?
110.
110. So what's the IQR?
118 minus 110. 8.
How much?
8.
118 minus 110, 8. Do we agree? So this is a much better measure of spread than the actual range itself. Of course, it's not the best, but it's certainly useful. So that's what we just did for this example. They recreated the box plot that we just saw, and they did that example here. Okay. So here we have an example. It talks about the heights of children of the same age. Now it mentions page 5, and that's a little off. It's actually on page, oops, hold on. 1 second, guys. I gotta figure out how to do this. Oops. Okay. How do you, oh, there's a way of,
Rotating.
there we go. Okay. So here we have the, this is for boys. Okay, what we have here is the stature for age percentiles for boys aged, looks like 2 years old to 21. Okay. Yes?
Yes.
So the next page is the same thing for girls. Okay, so we have it for boys and we have it for girls. Okay, so let's answer some questions and I'll walk you through how to do them for the first few. It says the heights of children of the same age are quite variable, which is not really a shock, I think. You know, I mean, kids are all over the place. Some are tall, some are short, right? This isn't new. Okay, so what is the approximate percentile for a 9-year-old girl who is 49 inches tall? So let's go to the girl chart, which is the second one here. 9-year-old girl who is 49 inches tall.
220. Oops, right. Sorry. Percentile for 49.
Like 54, I think, right?
Oh, so here's what we're gonna do. We're gonna go to the 9 inches. Sorry, 9-year-old girl, which is right here.
So you subtract.
Well, one second. I'll tell you.
Okay, sorry.
So here's 9 years. And then I go up to 49 inches, which is right there. Agreed? Now that point there is in between these two curves. So what do these two curves represent? Well, let's go and follow the curves to the end. And we see the upper of the two curve represents the 10th percentile, and the lower of the two curves represents the 5th percentile. So if I go back to 9 and 49, which is right here, what percentile would you say that corner point represents?
Fifth.
Yeah.
How much?
Fifth.
Percentile?
Well, it's not the 5th. The 5th is the 5th is down here. So I would say the 6th percentile is probably more appropriate.
Okay.
Does that make sense?
I thought we were subtracting. Am I confused? 10 minus 5? No.
I can't hear you. The sound is not good. What are you saying?
Is it 10 minus 5, or am I doing that wrong?
No, it's not 10 minus 5. This curve is the 10th. This curve is the 5th. We're somewhere in between. So the question is, where are we in between? Well, we're closer to the 5th, right? This point right here, the 949, wait, 9.
10th, isn't it?
Oh, it's actually more like the 7th or the 8th, right?
Right.
Yeah, I think I was looking at the wrong one. This point there looks more like the 8th percentile, maybe even the 9th percentile.
Need a magnifying glass.
Yes, no, maybe so. David?
Yes.
Is this making sense for everyone?
Yes.
I can see if I can zoom in a little more.
Oh, thank you.
So this is the corner right there.
There we go.
Yeah.
This is the corner right there,
Oh, yeah. So 49.
right? So this is the 5th percentile. This is the 10th percentile. So that looks to be a little more than halfway. I think the 8th percentile is probably the best guess. Okay. So the answer to this question is, what is the approximate percentile for a 9-year-old girl who's 49 inches tall? People are texting. We can. Yeah, Lori, it's a little hard to hear you today for some reason. Okay, so that will be the 8th percentile. Now, let's work a little differently. About how tall does a 12-year-old girl have to be so that she is as tall or taller than 75% of the girls her age? Well, that means she's at the 75th percentile. So we want to calculate the age for a 12-year-old girl at the 75th percentile. So I go to the girl chart, and here's the 12-year-old girl, and I go up, and I go up. Now, which curve, the first, the second, the third, the fourth, the fifth, the sixth, or the seventh? I have 7 curves here. Which of those curves represents the 75th percentile?
Fifth.
Fifth.
The 5th one. So 1, 2, 3, 4, 5. So I'm going to zone in to the 5th, which is right there. So how tall does she have to be in the 75th percentile? It looks like she has to be about 61 and a half inches tall. Right? Does that make sense?
But it's on 66.
What's on 66? This curve. This is the curve we're looking at.
The 75th one, right?
The 75th percentile curve. So it hits 12-year-old girls right there.
Oh, I think she's looking where it says 75th, exactly like right when it says it across, it says 66 inches.
No, the
Oh
70th.
no, okay, I got confused. Okay, so it touches the 75th one on the 6th around. Okay, I get it.
Okay.
So we need a ruler for this.
Yeah. So how tall does a 12-year-old boy have to be in the 75th percentile? Well, let's go to the boy chart, which is the first one. And we have 12, and we go up the first, second, third, fourth, fifth curve. And we are right there. So how tall does a boy have to be in the 75th percentile?
How, what did you say?
16.1.
16 and a
again?
half.
S- Can you please repeat the question?
How tall does a 12-year-old boy have to be in the 75th percentile?
About 60.
Around 60.8
Yeah,
ish,
60,
maybe 7.
60 and a half, it's 60.5, maybe 60.7, something like that.
Are you
I mean,
able to
yeah,
hear
you know,
me
six-
okay?
Say again,
I
what?
put 60.8.
Okay, that's fine.
Are you able to hear me okay?
We can hear you, but you're very soft for some reason. I don't know why. You're not your usual pervasive presence.
I think I
What did
jacked
I
up
hear?
my
What did you say here?
speakerphone.
I don't know. It's hard to say. All right, now, how can you tell from the chart when children are growing the fastest? If I look at this chart, whether it's boys or girls, how do I know when children are growing the fastest?
When they're at the 96th percentile.
No, if they're 96th percentile, that just tells us what curve they're on. That's not about when they're growing. I mean, we're talking about all people, all kids from the 0th percentile to the 100th percentile. When are they growing the fastest? What would you look for in the graph to determine when kids are growing the fastest?
The angle of the line. So like if, yeah, so I can't see the whole thing, but from the bottom of 32 up to where it starts curving is where they're growing the fastest. So from 2 to maybe
Well, that's just
15.
so here's their 2 years old and here they're
Yeah.
where are they growing the fastest? When they're 2 or when they're 20?
Almost 2 through 12.
2 through 12, yeah.
I didn't hear that.
2 through 12.
Yeah, like what? So are you talking about the lines going up?
I'm just curious. I'm just saying, what age does it appear that children are growing the fastest?
Ages 2 to 12?
Okay, what happens at 12 all of a sudden on the graph that tells you that it's not after 12?
Okay, no, not 12. Maybe.
I didn't say you were wrong. I'm just asking you to clarify.
Okay, but I understood your question. Okay, I would like to change that to 17 and at or 16, and then the
Percentile.
line curves. So if it curves, that means they're not growing anymore. They're just going on a straight line.
Okay, so
They're not going up. It's just curving.
welcome, Melissa. So yeah, so where the lines are steepest, which is what David, I think, was trying to say in the beginning with the angle. I think you were trying to say that, and then you kind of took a detour. But when the lines are steepest is when children go the fastest. And then what happens is that around, at least for boys, around 16 or 17, they kind of stop growing fast and they kind of taper off. Right? They're growing. You've had kids, you know this, right? They're growing, and all of a sudden they just kind of taper off. Girls are the same thing, right? They're growing fast, and then they bang, they taper off. Girls taper off around 13, 14 years old. That's when girls, for the most part, stop growing. Boys taper off 16 or 17. I'm not a physiologist. I don't know why. Girls grow faster in the beginning, and then boys take over. I don't know I don't know why. It's just the way it is. You know, I mean, sometimes in life, that's the answer. Okay. Is there more variability in the heights of 2-year-old girls or 14-year-old girls? So let's look at the 2-year-old girls. They basically range from what's to what in terms of the 5th percentile to the 95th percentile. What's the range of girls from the 5th percentile to the 95th percentile?
31 to like 36 inches.
Okay, so about 5 inches, right? They have a spread of about 5 inches. Would you say that?
Yeah.
Roughly, well, actually, it's less than that. It looks like it's 31.5 to a little under 36, right?
Yeah.
So it looks like about 4.5 inches is the differential of 2-year-old girls. In other words, unless they're abnormally tall or abnormally short, the bottom 5% to the top 5%, they're all going to be within a 4.5-inch range of each other. But what about 12-year-old girls? What's the variability in 12-year-old girls? From what to what?
$53-ish to like 64.5-ish. I don't know, you moved it, I lost my spot.
In
I'm
inches?
sorry. So I just want to check this was 12. So right here is 55
Okay, 55.
to 64 point something. We're talking about a 9-inch spread. Right? So 12-year-old girls, unless they're in the top 5 or bottom 5%, but the majority of them, the middle 90% have a 9-inch spread. So there's going to be a greater variability, which again, I think represents reality, right? And our experience. Okay. So there's a lot that you can get from these charts, correct? Now, let's compute the IQR of heights for 4-year-old boys. Let's compute the IQR of heights for 4-year-old boys. Well, obviously, we're going to go to the boy chart. Okay, where in the boy chart are we looking?
4-year-old boys.
4-year-old boys, which means we don't even care about anything else. That 4-year-old line is all that matters. All right, so here's the 4-year-old line. This one right here. And if we want the IQR, what does that mean? That means the Q3 minus Q1, right? Right, that's the IQR by definition, correct?
Yes.
So Q3 is the 75th percentile, and Q1 is the 25th percentile, right?
Mm-hmm.
Right, so the 25th percentile, 75th is which curve of the 7 curves that we have?
The 5th one.
The 5th one. The 25th percentile is which curve?
3rd.
3rd. So it's going to be the 5th curve minus the 3rd curve. So 1, 2, 3, 4, 5. That's Q3, which is about what, 41.5? Yes?
Yeah.
Okay. And then the 3rd curve is about 39.3. So it looks like, what's the IQR?
2.2.
About 2.2. Okay, about 2.2.
Question.
Yes.
How did you know that the Q3 was the 75th?
No, that's a definition. Q3 is the 75th percentile. We did that last time.
Yeah, okay. Thank you.
Okay, definition. So it says, write a sentence in context interpreting the IQR for 4-year-old boys. The middle 50% of 4-year-old boys have heights that range from, I don't even remember what it was, 39 inches to 41.5, whatever those numbers are. That's what I would say. The middle 50% range from this number to that number, because that's what the IQR measures, the middle 50%. Make sense? These curves are relatively easy to read once you've read them. Okay. So the IQR in the box plot. Okay, a box plot is, we've talked about this, a box plot is a way of recording data, or at least visualizing data. I think we did this example in the context of a different chapter, right? The name game, right? So which method would you choose as the most effective? The most effective method, I think, is the one that has the highest median. And the highest median is number 1, right? The median here is right here. Here's the median. Here's the median. So the first one has the highest median. It's the most effective. But which group has the most variability as measured by the IQR? 1, 2, or 3? Which of them is the highest variability as measured by the IQR?
Is it 3?
Well, the
Is it-
IQR is the box. So which one has the longest box?
Oh, the longest box 2.
2. Right? So 2 is the one with the greatest variability, the most spread out. And what is the IQR of 2?
And 35?
Approximately. Yeah, somewhere in the ballpark.
So 40 minus
3 minus 5,
5.
right? 35. I mean, I'm not saying it's exactly 35. I don't know the exact data, but it's certainly close enough that I wouldn't be surprised if it was that. Does that make sense so far?
Somewhat.
Yes, no, maybe so?
Maybe so.
Okay. So that takes care of the IQR. That's we did 2 of the 4 measures of variation. We did the range, we did the IQR. Those are done. Okay, range and IQR are finished. Now we're moving on to MAD, the mean absolute deviation. When I was a kid, my mother was a member of 2 groups. The first one was MADD. Anyone know what, Laura, you might know this. What is MADD?
Mothers Against Drunk Driving.
Mothers Against Drunk Driving. The other group she was a member of was DAM. Anyone know what DAM stands for? Mothers Against Dyslexia. No, that's funny because it's no one.
But
whatever.
I'm bummed.
Yeah, you know what? If you guys aren't laughing,
Yeah.
you just don't understand good humor. That's all I can say. That's all I can say. If you're not
Nope.
laughing,
I was
Don't-
gonna say dads against mothers, but yeah.
that's against
Yeah.
mothers.
Don't quit your day job.
Yeah, I'm thinking about it. But anyways, okay. All right. Okay. So one way to think about variability is how far, yeah, Angela, thank you. So funny. It really makes me feel so much better. How far each data point is from the mean. Okay. How far is each data point from the mean? So what we're going to do here is we are going to calculate how far each data point is from the mean. Well, before we can do that, we got to calculate the mean. So how do I calculate the mean of troop A here? These Girl Scout brownies, brownie girl, are all Girl Scouts brownies? I thought that was 2 different things. I don't know.
You're first a brownie and then you become a Girl Scout.
Oh, I see. I see. Brownies are good. I eat them a lot. I don't understand why they have the name brownie for Girl Scouts. Yeah, why do they have the name brownie for Girl Scouts? That's a good question. Nobody knows. Okay, whatever.
Nobody knows.
The brownies. So, troop A, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the mean of that?
$64? Oh, sorry, no. Never mind.
6.
6.
6. 6, right? 2 plus 3 is 5, plus 4 is 9, plus 5 is 14, plus 6 is 20, 27, 35, 44, 54 divided by 9 is 6. How about number B? Troop B, what's the mean? 2, 4, 6, 12, 18, 24, 33, 42, 4, 6, 12, 18, 26, 35, 44, 54 divided by 9 is how much?
6. They're all 6.
Again. 6 again. How about troop C?
6.
6 again. Now look at you. You're jumping ahead. How about troop D?
6.
They're all 6. Okay. And in fact, it says here, verify that the mean is 6 for all of them. So I didn't deliberately read that. I wanted you to do the calculations, but yes, they're all 6. Now, which troop already is closest to having an equal distribution? In other words, if I were to think that perfection is having one value at each, to have it all level, which group is currently closest to that ideal?
Troop D.
Actually, troop A is already there, isn't it?
Oh,
But I think maybe what they mean by an equal distribution.
because there's so many 6s.
Yeah, well, maybe what they mean by equal distribution, having all the values being equal. Maybe that's what they mean. Having all the values being equal. Which one is currently closest to having all the values being equal?
Maybe C.
Maybe C, right? I got a ton of 6s, got a 2 and a 10, but lots and lots of 6s. Okay, so we're gonna skip B because it's a waste of time. But notice here, just first of all, they organized all 4 of them into dot plots, one dot plot on top of each other. Here are the number of boxes, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's troop A, troop B, troop C, and troop D. We see troop A has 1, 2, 1, 3, 1, 4, 1, 5 all the way through. Troop B has 3 here, a couple here, 1 here, a couple there, 1 there. Troop C has this, lots of stuff. Oh, okay. Here's what we're gonna do. Let's look at troop A for a second, which was 2, 3, 4, 5, 6, 7, 8, 9, and 10. What was the mean again? I forgot. My memory is bad today. Well,
6.
okay, X bar is equal to 6. Okay, of course I knew that. It says it right here. The mean is 6. How far is 2 from 6?
What do you mean, how far?
How many numbers away from 6 is the number 2?
Oh,
4. 4.
4. How about the next one? 3. How far from 6 is it?
3.
3. How far is 4 from 6?
2.
2, and then 1, and then 0, and then 1 again, and then 2 again, and then 3 again, and then 4 again. If you add them all up, what do you get?
20.
20. So for troop A, when we do this, we get a value of 20. Let's do it for troop C. Remind me again, what was troop C? Troop C was
6.
2 tons of 6s and a 10.
And a 10. 2 and a 10.
Okay, 2 tons of 6s and a 10. So let's just write it
2
down.
and a
Got
10.
2, lots of 6s. There were 7 6s and a 10. Now, how far away is 2 from the mean?
4.
4. How far away is 6 from the mean?
0.
0.
Still 0. And still
0, 0,
Still
0.
Still 0. And still 0. How far away is 10 from the mean?
4.
4.
4. So a total value of what?
8.
8. So based upon this method of variability, it seems that that troop C is less variable than troop A because the distances from the mean overall are smaller. Okay, in the first case, we get a total of 20 when we look at all the distances from the mean. And in troop C, we get a value of 8. 8 is certainly smaller than 20. So troop C is less variable than troop A. Okay, so is the distribution of troop A or troop C more variable? Troop A was more variable because it had a higher number. Okay, with me so far?
Sort
Yes.
of.
Well, sort of I don't like. I'm always more than happy to go over things and explain things again, but I need someone, I need you to say exactly what the issue is. I'm always
So
like-
so it says, is the distribution of troop A or troop C more variable?
yes.
And the reason it's more variable is because,
Oh, the reason what's more variable?
what?
You said it's. What is it's? The reason what's more variable?
Well, I'm reading the question. Is the distribution
And you
of troop
said,
A or troop C more variable according to the method devised by these students?
right, and you said it's more variable, and I said, what is it's referring to?
Oh, troop A, you said has a higher number
Right, the total
of
troop A-
variable.
Well, no, not a higher number of variable, the higher number by this method, right? This method is
Oh,
constructed, troop A gets the higher number than troop C. So these students would claim that troop A is more variable because it had the higher number.
oh, has
Okay,
a higher number.
we're trying to see whether or not this method of theirs makes sense. Okay, so right now what they're concluding is that troop A is more variable than troop C because this number that they computed is higher. Okay, and the question is this a valid approach? Well, let's look at another example.
I have a quick question. I'm so
Yes,
sorry.
go ahead, of course.
For variable, I understand completely that it's troop A is higher because we did the whole math and stuff, but I don't understand why you say variable. I don't know if you said that and I just didn't hear it.
More variable means it varies more.
Oh, got it. Okay, thanks.
Not like a variable like X is a variable.
Yeah.
Oh, I
More
was thinking
variable,
that.
it varies more.
Okay, got it. Makes more sense. Thank you.
So here we have another one. We have troop E. Now troop E is a little different than troop A, B, C, and D because troop E is a very popular, Girl Scout troop. They have 40 students or 40 members instead of 20. So they're very popular. And when you look at them, you notice them. Okay, you notice that all of them or 20 of them sold 5 and 20 of them sold 7. Now the mean is 6, right? Because by symmetry, if here's 5 and here's 7, they're the same height, right? The balance point is going to be right in the middle at 6. So the mean is still going to be 6. But let's compute the value that we would get by this process that the students devised. Okay, how far is this one here from the mean?
1.
1. And how about this one here? 1. And how about this one here? 1. And they're all 1 away from the mean, correct?
Yeah,
So when I add up all 40 of them, what do I get?
40.
40. Now, that's bigger than 20. So would you say that this data is more variable than A? The number's higher. So the student's method, which is count up these values, it seems to get that A is more variable. But A certainly doesn't look more variable. So what is wrong with the student's idea and how can we fix it? What is wrong with the student's idea and how can we fix it? The reason the student's idea is wrong is because what the students neglect to take into account is that the sample size here, there's 9 Girl Scouts, and here there's 40 Girl Scouts.
Is it like that weighted mean kind of, the
Well,
weighted GPA kind of thing? If you
kind of-
have more Girl Scouts, you should sell more cookies or
Yeah,
whatever.
if you have more Girl Scouts, you're probably going to sell more cookies, but more importantly, when you add up how far each one is from the mean, you're adding more numbers because there's 40 girls instead of 9. So it makes a lot of sense that it's going to be higher because you're adding more. So how do we take into account? How do we fix it? The answer is very straightforward. After you add them up, you go ahead and you divide by how many. So at the end, you say you take that number, which is what you get when you add them all together, and then you divide by how many you have. So in the first case, we got 20. But when we divide 20 by 9, what does it become?
20 divided by 9. It's a decimal. 2.2 bar.
2.2 bar. And when you divide 40 by how many Girl Scouts there were in that case, which was 40, you get 1, which is a lot smaller than 2.2 bar. Okay, so the fix is to divide by how many there are. When you do that, you get a perfectly valid measure of variability, and that is called the mean absolute deviation, or the MAD. Okay, the mean absolute deviation. Now, as wonderful as the MAD is, it's never used in practice.
Never
It's
used where?
never used in practice. You'll never find the
Oh.
MAD used anywhere in any research journal or statistical computation anywhere on the planet. Okay, it is used as an introduction to variability, because the true one that we use, which is the standard deviation, is a little more complicated, but comes from the same place. So what do we do for the standard deviation? Well, again, we compute how far each one is from the mean. We start in exactly the same place. You compute how far each one is from the mean. But this time, you don't just add them. This time, you first square them all.
Square them.
And then add them.
Square root them.
Well, you first square them all. You then add all of those together, like the math, but you're not adding the individual deviations. You're adding the squares.
Yikes. Are you going to do an example?
I'll do it
Thank
again.
you.
I'll do an example. And then you don't divide by the number of data points. You don't divide by n. You know, if there's 9 Girl Scouts, you wouldn't divide by 9. What would you divide by?
Well, according to that,
Yeah, according to this, what would you divide by?
8.
8, exactly. You divide by 1 less than the number of data points. Okay, you divide by 1 less than the data points. And then finally, what's the last step?
Square it.
No, not square it,
Square
or
root.
root it.
Square root it, sorry.
So let's do an example. Let's do the same example that we were doing before. Girl Scout Troop A. First, the mean was 6. That part hasn't changed, right? The mean is 6. So how far is 2 from 6?
4.
4. Technically, in this case, it's -4, but we're going to square it anyway, so it doesn't really make a difference. How far is 3 from 6?
3.
3. How far is 4 from 6?
2.
5,
1.
6, 7,
0,
8, 9, oops,
2,
and
3.
4. The reason why
What
these
is-
are the reason why these are negative. That's I'm gonna fix that. That's a bad. Oh, undo. I'm gonna fix this one here. Oh, hello. That was nice. Oh, shaka. So the reason why these are negative is because the data point is less than the mean. X minus X bar is negative. These are positive the other way around. But who cares? I'm gonna square them anyways. What's -4 quantity squared?
16.
16. What is? Oops. What is -3 quantity squared?
9.
9. And what's -2 quantity squared?
4.
And 1 and 0 and 1 and 4 and 9 and 16. So the first thing we do is we calculate how far each one is from the mean, just like we did for the MAD, but this time we square them all. And then we add. What do we get?
32, 30, 36, 38, 40, 42, 44, 45, 46, 49. Did I do that? Oh, 60, sorry.
Let's see. 16 and 4 is 20.
Was
9
doing
and
the
1 is
math.
10. 16 and 4 is 20. 9 and 1 is 10. So 20, 40, 56. All right, no one says go in order, right? Look for shortcuts. 16 and 4 is 10. 9 and 1. 16 and 4 is 20.
Common Core.
60.
Okay, so we did the top, which is we squared them all and we added them all together. Then we divide by what number?
8.
8. And we get 2.74. That is the standard deviation of the data.
What did the sigma stand for again?
It means add up.
Okay.
Take all these squares and then add them all up.
What is the common use of standard deviation in life?
Well, it's used in any statistical study anywhere on the planet.
That's broad.
This is the one that's used.
Huh?
This is the one that's used. Okay, we don't use the MAD. We very rarely use the IQR, although we do sometimes. The standard deviation is really the big one. Now, the first question you should ask is, why do we divide by n minus 1 and we don't divide by n? The answer is complicated. Okay, but the problem is that your students are going to ask it. And therefore, you have to come up with an answer for them. So here's an answer you can give. Okay.
Because that's just the way it is. No, I'm just kidding.
Well, no, you never want to say that in math. You never want to say that as a teacher.
I'm just kidding. I have to switch from mom to teacher now.
I understand. Shut up and go to your room. Okay. You guys ever? Well, when class is over, I'll show you guys a 3 or 4 minute clip. Actually, you know what? No, I'll show it after class is over. I want you all to stay to watch this lovely clip. That's really funny in my opinion. But you just reminded me of it, so I'm going to play it after class is over. So here's the answer. Suppose I were interested in the average height of every American. So I'm going to go to CSUN when the pandemic is over. And I'm going to measure the height of every CSUN student. Now that's 40,000 students. So I'm going to measure the height of 40,000 students. And I'm going to take the average of my 40,000 sample and say, you know what? I think that the average height of every American is really close to this value. Would that be a good approximation, would you say? Is there something inherent in the CSUN sample that should indicate that it's not representative of the entire population? Do tall people not go to CSUN, or short people? Or, I mean, there's no reason why it should be representative, correct?
Right.
But let's say instead I do the following. I take the same sample of 40,000 students, and I say, you know what? I'm going to take the tallest person in my sample and use that as my approximation for the average height of every American. Would that be a good representation? If I use the tallest person in my sample to represent America, does that seem reasonable that I should be close to the true value? No, because CSUN has a basketball team. So there's going to be people who are like close to 7 feet tall. And therefore, if I take the tallest one at 7 feet, let's say, that doesn't really seem reasonable, correct? But it still is an approximation. It's just a bad one. Why is it a bad one? Because I don't expect it to give the value that I'm looking for. We call that a biased estimator. It's biased in one direction versus the other. When you divide by n instead of n minus 1, you are getting a biased estimator for the standard deviation. It is biased for reasons that I can't explain, okay? Just accept it, go to your room and eat your dinner, okay? At some point in statistics especially, you just gotta say, I can't explain why right now, just go for it or go with it.
You'll find out later.
Yeah, you'll find out later. If you divide by n, it's biased. If you divide by n minus 1, it's not biased. For very complicated mathematical reasons. So you can also say if the number is really large, it doesn't really matter. If you divide by 1,000,000 versus 1,000,001, or 1,000 versus 1,001, you're not, I mean, pick a number, divide by 1,000, and then pick the same number, divide by 1,001. You're going to see in your calculator that it's not really much different. So if the sample size is large, who cares? But just be aware that dividing by n is biased and dividing by n minus 1 is not biased. Okay? You go ahead.
This may seem kind of like maybe my brain isn't processing things properly. So basically, say we have an outlier. By subtracting 1 from n, we're subtracting that outlier?
No, n is the number of data points. N is how many data points there are.
Okay.
Right? So if there's 100 data points and one of them's an outlier, I'm not subtracting from the outlier. I'm just taking 99 data points instead of 100. Or I'm just using 99 instead of 100. But it's not about which data point it is. It's about the total number of data points.
Okay, thank you.
Okay. What we do next will take a little too long, and I'm not going to finish it today. So I want to show you a cute video to make everyone laugh and smile. And we'll finish this next time. But I hope you like it. And from what I remember, it's clean. So I really remember it being clean. I really hope it is, because I don't want to get in trouble showing you a language, you know, something that has bad language. But hopefully you find this amusing, because I found it amusing. So I'm going to share my screen, and I hope you all enjoy this. If you can hear, let me know.
Are you going to continue to keep recording?
Yeah, why not? It's part of the lecture.
Okay.
In terms of, well, yeah, why not? Can you all hear this? Okay. It's a cute little thing.
If it's him, it's already going to be bad.
Papa, can you play outside?
No,
Why?
because it's 5 o'clock in the morning. It's too early.
Why?
The sun hasn't come up yet.
Why?
Because the sun comes up later.
Why?
Well, the Earth goes around, and when it turns a certain amount, the sun shows on the horizon.
Why?
I don't know.
Why? Why don't you know, Papa?
Because I didn't pay attention in school, okay? I didn't
Why?
because I was high all the time. I smoked too much pot.
Why?
Hey, I didn't think it would matter.
Why?
I just figured my life would come together on its own.
Hmm.
I met your mom. You came along. So now I work at the muffler shop. Well, it's too late for me to pursue a career now. And since your mom has a job with benefits, I stay home and I take care of you. Because what I make is pretty much just a joke. Well, the service economy replaced manufacturing. There's no real jobs in America anymore. We had good jobs for a while, but it's just because we were lucky, and now we're unlucky.
Why?
It's just the way it goes.
Why?
Because God's dead and we're alone.
Okay.
Anyways, I thought that was kind of amusing. But anyways, so everyone, we're done for today. I hope you had a wonderful time. Angela, you're wearing a Santa Claus hat. I just noticed. Are you Santa Claus?
I'm Mrs. Claus.
Mrs. Claus. Oh, so if I want something from Santa, can I ask you and you put in a good word?
If I don't have to take another test or quiz, yeah.
Yeah, so that I'm gonna be a bad boy and say no this time around. So
Thanks for getting us in the spirit of things, though.
yes, go. Of course, I'm Jewish, so I'm not sure what you're trying to say, but
Happy Hanukkah.
happy Hanukkah. You're gonna say
Hanukkah.
Hanukkah. Anyways, everyone, have a great everything and happy holidays and whatever you believe, whether it's God, Jesus, the great turtle in the sky. Everyone has their beliefs. It's all good on my end. I don't care. Let's all rejoice together and be happy with our beliefs and have a wonderful time.
And don't be a super spreader.
Don't be a what she said. I don't know what that means. But,
Why did that sound wrong?
huh? Oh yeah, the quiz. So I didn't put the quiz up, but I will put it up for the weekend. The quiz that I was going to do last time that I forgot because I was going to be putting up all the videos. It will come up. You don't have the weekend to do it.
Remember, it's chapter 10.
Chapter 10, yeah, chapter 10. I got chapter 10. Okay. So
That's quiz number 4, right?
What was that?
That's quiz number 4?
And quiz number 5, I think.
5.
Yeah. I think it's quiz number
5. What the heck happened to quiz number 4?
It's been up there for a while.
Oh, I missed the day.
In class. I don't think I can go over. Yeah, exactly. So everyone, I will have a great weekend, and I will see you all on Tuesday. Peace out, everyone.
Thank
Bye.
you.
Thank you.
Bye. Miss you.
Oh, miss you already. Thank you so much.
Bye.